In computational complexity theory, NP is one of the most fundamental complexity classes. The abbreviation NP refers to non-deterministic polynomial time. Intuitively, NP is the set of all decision problems for which the instances where the answer is yes have efficiently verifiable proofs of the fact that the answer is indeed yes. More precisely, these proofs have to be verifiable in polynomial time by a deterministic Turing machine. In an equivalent formal definition, NP is the set of decision problems where the yes instances can be accepted in polynomial time by a non-deterministic Turing machine. The equivalence of the two definitions follows from the fact that an algorithm on such a non-deterministic machine consists of two phases. The first of which consists of a guess about the solution, which is generated in a non-deterministic way, while the second consists of a deterministic algorithm that verifies or rejects the guess as a valid solution to the problem. The complexity class P is contained in NP, but NP contains many important problems, the hardest of which are called NP-complete problems, whose solutions are sufficient to deal with any other NP problem in polynomial time. The most important open question in complexity theory, the P equals NP problem, asks whether polynomial time algorithms actually exist for NP-complete, and by corollary, all NP problems. It is widely believed that this is not the case. Formal definition. The complexity class NP can be defined in terms of NTIME as follows. Alternatively, NP can be defined using deterministic Turing machines as verifiers. A language L is in NP if and only if there exist polynomials P and Q, and a deterministic Turing machine M, such that for all x and y, the machine M runs in time P on input. For all x in L, there exists a string y of length q such that M equals 1. For all x not in L and all strings y of length q, M equals 0. Introduction. Many natural computer science problems are covered by the class NP. In particular, the decision versions of many interesting search problems and optimization problems are contained in NP. Verifierbased definition. In order to explain the verifierbased definition of NP, let us consider the subset sum problem. Assume that we are given some integers, such as -7, -3, -2, 5, 8, and we wish to know whether some of these integers sum up to 0. In this example, the answer is yes, since the subset of integers -3, -2, 5 corresponds to the sum plus 5 equals 0. The task of deciding whether such a subset with sum 0 exists is called the subset sum problem. To answer if some of the integers add to 0, we can create an algorithm which obtains all the possible subsets. However, notice that, if we are given the particular subset, we can easily check or verify whether the subset sum is 0, by just summing up the integers of the subset. So if the sum is indeed 0, that particular subset is the proof or witness for the fact that the answer is yes. An algorithm that verifies whether a given subset has sum 0 is called verifier. More generally, a problem is said to be in NP if there exists a verifier V for the problem. Given any instance I of problem P, where the answer is yes, there must exist a certificate W such that, given the ordered pair as input, V returns the answer yes in polynomial time. Furthermore, if the answer to I is no, the verifier will return no with input for all possible W. Note that V could return the answer no even if the answer to I is yes, if W is not a valid witness. For example, in the subset sum problem, if there is a subset whose sum is 0, but we select W to be a subset whose sum is not 0, the verifier will return no, while if there is no subset whose sum is 0, the verifier will return no, regardless of the choice of W. The verifier needs only polynomial time, so the subset sum problem is in NP. The no answer version of this problem is stated as Given a finite set of integers, does every non-empty subset have a non-zero sum? The verifier-based definition of NP does not require an easy-to-verify certificate for the no answers. The class of problems with such certificates for the no answers is called co-NP. In fact, it is an open question whether all problems in NP also have certificates for the no answers and thus are in co-NP. Machine definition equivalent to the verifier-based definition is the following characterization. NP is the set of decision problems solvable by a non-deterministic Turing machine that runs in polynomial time. This definition is equivalent to the verifier-based definition because a non-deterministic Turing machine could solve an NP problem in polynomial time by non-deterministically selecting a certificate and running the verifier on the certificate. Similarly, if such a machine exists, then a polynomial time verifier can naturally be constructed from it. Examples: this is an incomplete list of problems that are in NP. All problems in P. The decision problem version of the integer factorization problem. Given integers n and k, is there a factor f with 1 less than f less than k in f dividing n? The graph isomorphism problem of determining whether two graphs can be drawn identically. All NP-complete problems, e.g., a variant of the traveling salesman problem, where we want to know if there is a route of some length that goes through all the nodes in a certain network. The Boolean satisfiability problem, where we want to know whether or not a certain formula in propositional logic with Boolean variables is true for some value of the variable's properties. NP is closed under union, intersection, concatenation, clean star, reversal, disambiguation needed. It is not known whether NP is closed under complement. Why some NP problems are hard to solve. Because of the many important problems in this class, there have been extensive efforts to find polynomial time algorithms for problems in NP. However, there remain a large number of problems in NP that defy such attempts, seeming to require superpolynomial time. Whether these problems are not decidable in polynomial time is one of the greatest open questions in computer science. An important notion in this context is the set of NP-complete decision problems, which is a subset of NP and might be informally described as the hardest problems in NP. If there is a polynomial time algorithm for even one of them, then there is a polynomial time algorithm for all the problems in NP. Because of this, and because dedicated research has failed to find a polynomial algorithm for any NP-complete problem, once a problem has been proven to be NP-complete, this is widely regarded as a sign that a polynomial algorithm for this problem is unlikely to exist. However, in practical uses, instead of spending computational resources looking for an optimal solution, a good enough solution may often be found in polynomial time. Also, the real-life applications of some problems are easier than their theoretical equivalents. Equivalence of definitions. The two definitions of NP as the class of problems solvable by a non-deterministic Turing machine in polynomial time and the class of problems verifiable by a deterministic Turing machine in polynomial time are equivalent. The proof is described by many textbooks, for example Sipps's Introduction to the Theory of Computation, section 7.3. To show this, first suppose we have a deterministic verifier. A non-deterministic machine can simply non-deterministically run the verifier on all possible proof strings. If any proof is valid, some path will accept. If no proof is valid, the string is not in the language and it will reject. Conversely, suppose we have a non-deterministic trademark called A accepting a given language L. At each of its polynomially many steps, the machine's computation tree branches in at most a constant number of directions. There must be at least one accepting path, and the string describing this path is the proof supplied to the verifier. The verifier can then deterministically simulate A, following only the accepting path, and verifying that it accepts at the end. If A rejects the input, there is no accepting path, and the verifier will always reject. Relationship to other classes. NP contains all problems in P, since one can verify any instance of the problem by simply ignoring the proof and solving it. NP is contained in PSPACE. To show this, it suffices to construct a PSPACE machine that loops over all proof strings and feeds each one to a polynomial time verifier. Since a polynomial time machine can only read polynomially many bits, it cannot use more than polynomial space, nor can it read a proof string occupying more than polynomial space. NP is also contained in the XPTIME, since the same algorithm operates in exponential time. The complement of NP, co-NP, contains those problems which have a simple proof for no instances, sometimes called counterexamples. For example, primality testing trivially lies in co-NP, since one can refute the primality of an integer by merely supplying a non-trivial factor. NP and co-NP together form the first level in the polynomial hierarchy, higher only than P. NP is defined using only deterministic machines. If we permit the verifier to be probabilistic, we get the class MA solvable using an Arthur-Merlin protocol with no communication from Arthur to Merlin. NP is a class of decision problems. The analogous class of function problems is FNP. The only known strict inclusions came from the space hierarchy theorem and the time hierarchy theorem, and respectively they are NP-NEXPTIME and NP-XPSPACE. Other characterizations. In terms of descriptive complexity theory, NP corresponds precisely to the set of languages definable by existential second-order logic. NP can be seen as a very simple type of interactive proof system, where the prover comes up with the proof certificate and the verifier is a deterministic polynomial time machine that checks it. It is complete because the right proof string will make it accept if there is one, and it is sound because the verifier cannot accept if there is no acceptable proof string. A major result of complexity theory is that NP can be characterized as the problems solvable by probabilistically checkable proofs where the verifier uses random bits and examines only a constant number of bits of the proof string. More informally, this means that the NP verifier described above can be replaced with one that just spot checks a few places in the proof string, and using a limited number of coin flips can determine the correct answer with high probability. This allows several results about the hardness of approximation algorithms to be proven. Example: the decision version of the traveling salesman problem is in NP. Given an input matrix of distances between n cities, the problem is to determine if there is a route visiting all cities with total distance less than k. A proof certificate can simply be a list of the cities. Then verification can clearly be done in polynomial time by a deterministic Turing machine. It simply adds the matrix entries corresponding to the paths between the cities. A non-deterministic Turing machine can find such a route as follows. At each city it visits, it guesses the next city to visit, until it has visited every vertex. If it gets stuck, it stops immediately. At the end it verifies that the route it has taken has cost less than k in no time. One can think of each guess as forking a new copy of the Turing machine to follow each of the possible paths forward. And if at least one machine finds a route of distance less than k, that machine accepts the input. A binary search on the range of possible distances can convert the decision version of traveling salesman to the optimization version. By calling the decision version repeatedly,